So open source TIG-based metal 3D printing, um, it's definitely a novel topic. Metal 3D printing, though it is novel compared to just like FDM, it's not extremely novel. It's very commercial and it's not super uncommon. Uh, but my PhD research was partially on was open source TIG-based metal 3D printing. And as you'll see, there were all sorts of other offshoot projects that kind of happened, but they were all kind of components that were to be used for metal 3D printing because that was kind of the task that I was given. But the big thing is this idea of things being TIG-based, which I'll get what that means, or I'll get to what that means in a little bit. Yeah, so my kind of thesis, or what my guiding thing was, a TIG welder could be paired with open source hardware and tuned with particle swarm optimization to yield a substantially lower cost solution for metal additive manufacturing. So metal additive manufacturing is very expensive, like laser sintering, very expensive. So yes, and we know that open source solutions can be much cheaper than closed source solutions. So, kind of the big picture, the things that I was doing, I had to make the optimization algorithm work. And so, of course, I tested it first. I didn't go right to the really hard thing of doing the metal printing, but I did it on some kind of hard plastic. And also, there was the hardware associated with it. I created some data acquisition hardware and the printer itself, and then characterized it and kind of saw how things were working given the actual the design. Yeah, so I created this software for implementing particle swarm optimization to optimize pretty much anything, but specifically I wanted to optimize parameters for 3D printing, because when you start off with something novel, sometimes it can be hard to guess what the exact parameters are. Sometimes you can calculate them, sometimes you can't. And so this software was used to aid that. And before I even did anything physical, I tested on these basically test functions like the Goldstein-Price function to see if I could optimize this. These functions are kind of goofy looking plots, but they have a known minimum, and so you want to see if you can find those minimums as well. And I was able to, so that's a good thing, right? Obviously this is a single slide, but this was, a couple months, maybe not a couple months, but it was a lot of work to get to that point, and there was a lot of like, oh, it's not actually working right. Anyways, yeah, and then we took that and wanted to use it on kind of a challenging use case, and that was printing low density polyethylene. It was recycled, so there was other stuff mixed in, and it's just a pain in the butt to print, but it's very common, and so if we could print new furniture with it or things like that, that would be great. So this was one of those things like, we have to validate the algorithm, and it'd also be nice if we could print with this material, so let's test it out. So that's why we didn't go right to the metal. We validated on something that would likely be a little bit easier. Yeah, and so the optimizations shouldn't be a surprise that you start in one dimension, then go to 2 dimensions, and then 3 dimensions. And so the way that particle swarm optimization works is you would print some of these lines and you would characterize and see, are the lines good or bad? Basically just like diving judges, how they hold up their signs for 10 being the best, 1 being the worst. Or I don't know, maybe it starts at 0. Anyways, so it would be that same thing where you would say, oh, it's really lumpy, or oh, it's a little shorter, or it's not as wide as it's supposed to be. All those factors would come in and quantify if the line was good or bad, and then those parameters would inform the next generation of tests and next generation, so on and so forth. And then that final output would inform how to start with the single plane, and then that output would inform how to start with the cube or some 3-dimensional object. So that was all optimization, right? I did that for the plastic and also for the metal. Yeah, and then the other thing that was kind of a side creation was this BREAD system. It stands for Broadly Reconfigurable Expandable Automation Device. And the idea was, if you've ever worked with National Instrument systems, you've probably seen their like data acquisition, like their like the C-RIO or the C-DAC, where they have these cards that you can put in, and they all have different functions. And I wanted to make an open source version of that, because I found that I was making all sorts of different designs, and then I would have to like tweak them for somebody else and tweak them and add this other feature and all that. And so instead, what I wanted to do was make this system where I could just plug things in, and all of a sudden I'd have a customized system that could do basically whatever I needed without having to do a bunch of redesign. And so yeah, this is just some of the connection schemes. Like you could just connect to a single slice, and maybe this slice is made for analog readings, maybe it's made for temperature readings, whatever. Maybe it's a motor controller, or maybe you need multiple ones. So maybe you have a motor controller and a thermocouple, right? So you can read temperatures, and maybe you have another custom slice that hooks to microphones, things like that. And you could even, so this was a loaf going with the bread theme, and then you could connect even more, up to 8 loaves. So yeah, that was, this was something that, once again, was kind of a discovery that I just wanted to make just for the sake of me having it, but it was also going to be useful for the metal 3D printing. Yeah, so the slices that I'd made at the time of publishing was things for analog measurement, digital input-output, audio analysis, measuring current, controlling relays, controlling steppers, reading temperatures, communicating through USB, things like that. Yeah, and so there's lots of use cases, all sorts, right, for automation, data acquisition, power analysis, all sorts of things. But specifically, I was using it for metal 3D printing, right? So if you're going to be doing these experiments, it makes sense that you'd want to try and get as much data as you can, right? Get as much data as you can. And so I actually only really needed 2 slices. I needed a low voltage AI sensor, so that's analog input, and so that was enabled me to take microphone measurements, light measurements, and current measurements, and then I could also take temperature measurements with the thermocouple cards. And this was just kind of the loop, right? It would just constantly sample and just keep sampling and report forever, essentially. Yeah, so welding, I'm not sure if all of you have seen someone weld before, but right, there's some sort of high intense energy input that causes the metal to melt and fuse together. That's usually what you have. And so a human being, when they're welding, right, the signals they have to know if their settings are right is they can tell kind of how the light's flashing. If it's sputtering a lot, that's a bad sign normally. Same thing with the light. There's usually a sound. It's kind of like a stuttery sound. So that's usually not good either. And also the power input, which is something that a human might not necessarily have a feeling for, but usually that's kind of an extra thing that we can get. And if we see that that's really stuttery or spiky, that means that there's probably some welding. It's not as smooth as it could be. And also, so those are the 3 sensors that I really used to quantify if a weld was good or bad. And so that was kind of cool because, right, the idea was we would take these measurements as we were running our optimization, and after our optimization, we would give a score to a weld and say, this weld was good, this weld was bad, and we also know what the sensor data looked like for a weld of a good score or a weld of a bad score. So that wasn't anything that I ended up doing anything with because I didn't quite have the time, but that data set is there now for us to work with. And of course, I also took some temperatures. So just to kind of highlight that, this is the sound spectrum, right? So this is, right, this x-axis is frequency of the sound, and then the magnitude, right, is in decibels. And so you can see a good weld had a spectrum that looked like this, right? This blue line, and a bad weld had this orange line here. And so you can see like the biggest thing is on this low frequency side, there was a big difference. And so that would be kind of the big thing to look for is if this difference is big, that means it's probably a bad weld. And also there was a pretty clear difference with the bad weld in the light spectrum too, the light turning on and off, turning on and off. Obviously this isn't the actual frequency of the light carrier, right? It's like the light turning on and off and being present, not present, that type of thing. And so you can see there's also a big, clear difference there. Oops, wrong line. Yeah, so the novel thing about this printer is it was using a TIG welder as its deposition method, right? So TIG stands for tungsten inert gas, and it's done by generating a high current arc, and then that arc has a lot of energy with it, and you place the filler in the path. And so that filler melts and basically adheres or becomes one with all of its surroundings, as long as it's a like material. So why did I want to use TIG? Well, it's because my advisor told me to, but also some of the justification for it was TIG is generally used for intricate welding work, right? So for really fine things, and we want to have fine resolution with that 3D printing. Other welding methods are normally much thicker than what you would get with TIG. And so you can deposit small and very smooth beads, which is usually desirable. And there's pretty much no splatter associated with TIG, where other welding methods like MIG will kind of get splattered all over the place, and that can add up, especially when you're doing infill patterns. That can be really annoying. And TIG has no preference of filler material, meaning that you could say, all right, we're going to do this with brass now, or we're going to do it with any other material that's conductive to a point. Like you probably wouldn't be able to do like titanium, maybe, I don't know. Anyways, but we were doing mild steel. Yes, so the drawbacks, there were two big drawbacks with this. So one, so you can see kind of, and I'll get to the actual, what the mechanism looks like. But you can see here's a TIG torch, and there's so there's an electrode right there, and the material being deposited underneath of it. That's kind of what it's set up to do there. Anyways, so when this torch builds up the energy to create an arc, to break down the gas in between it and the metal that it's trying to conduct to, takes a lot of energy, and when that energy is released, finally, when it builds up enough potential, it generates something called an electromagnetic pulse, right? So an EMP, you guys have all heard of those. It's like, oh, the AI apocalypse and robots are taking over. All we need is EMPs to kill them, right? That type of sci-fi thing. But it totally is a real thing. And so having this device mounted to your printer that is controlled by electronics, it's basically it can self-destruct if not handled properly. When I was early in this research, I actually broke my computer by having it too close to this for too long. So it's totally a problem that needed to be addressed. And the other thing is basically there's only one direction you can print, and that's this way, right? So that's filling in, because you can't deposit over already deposited material unless you raise yourself up. And so this can only print in one direction, which isn't necessarily a problem, but it's definitely unique compared to other printers. Yes, so the EMP problem is reasonably easy to solve, right? All it took was a big metal cage called a Faraday cage to nullify the effect of that EMP. And so that also could work for fume extraction, which was nice. And so it's basically just a big metal box. And yeah, so it mostly worked. There were like some conditions, but that was basically when I had the wrong parameters for my welding, that it could still cause the board to turn off. It would never break it, but it would cause it to like restart. Yeah, so the extrusion device, it looked like this. And so, right, we had a torch right here, and this was the extrusion motor. So this was just repurposed on a Lulzbot TAS. I just took the connector for the regular extrusion motor and hooked it into this new end effector, and that would go through this feeder tube and print out. And so this is made to be as adjustable as I could make it, right? So I could bend this tube to change the feed angle of the material. I could also place some washers under the plate that held the torch on there, so I could change the torch angle, because all those were important. Because the angle of this relative to this and where they feed in, it was all very important. Some other important construction things, or like I said, I used an old Lulzbot TAS. I just modified it because we wanted to make this as low cost as possible. But that meant all these parts in here, they were all plastic, right? A bunch of 3D printed parts. And welding also puts off a lot of UV light. That's why you usually have to wear like a welding mask. Anyways, and so that can damage plastics over time. And so we put some reflective kind of white outdoor paint over everything just to protect the parts. And I also created this isolated bed because we wanted this to be on a separate ground than the rest of the printer, because in the case that the current did go through the printer rather than where it's supposed to go back to the welder, things would certainly toast. And so everything was isolated by these little plastic washers, and there's no continuity. And so you've seen this before too, right? I used a solid state relay that was hooked to a fan output, essentially. So the controller went to the solid state relay, and that was what was triggering the welder to turn it to tell it to be on or off. Yes, so the machine was pretty novel at that point, even though it was still just basically a 3D printer. And there were all sorts of the tests that I had to do for the optimization that had to be ran over and over and over and over and over and over again. And so instead of writing G code by hand, I modified this. Well, I made this entire software here. I called it Lightning. I made this little area here where I could automatically put in parameters for the test and just run the G code, and it would kind of fill in the blanks for the G code and run it. So that meant that we could run these tests really, really fast. And of course, you can see, right, the TX and RX, and you can see like some of the OKs in there from the printer saying, okay, I turn things on or turn them off, whatever. I also had things like jogging, homing, things like that, or I could run a G-code routine if I needed to. So yeah, making a custom software was pretty much essential to be able to do this in any quick way. Yeah, so like I said, the extruder definitely has limitations, right? So this is printing in the favorable direction, and this is printing in 45. This is 45 in the other direction, and this is up and down. And yeah, the depositions were all pretty bad besides for this. And even at this point, this wasn't really good parameters, but you can see it clearly has a deposition here. Everywhere else is kind of a little crappy. So yes, the direction is left to right only. Yes, so we printed lines, and we're able to get a pretty decent line. And the microstructure that we got was very good. There's some porosity at the very top, which is something you don't want. Obviously, you want it to be metal, solid. But the interface is pretty good. There was no what's called cold lapping, or like the edge will kind of like be like a droplet shape, and it won't like. This looks good, right? So this looks good because it's fully adhered to the substrate. And so after that, we did some planes. So you can see here, here's a decent plane. And compared to what we started off with, this was a really good plane. And then we started doing prisms. Yeah, so the prisms, admittedly, they turned out better. You can see this one was one I was trying to picture here. They turned out okay, but not as good as I would like. So the conclusion of this whole research is there's totally a lot of work left to be done to get this to be a really like consumer product level. But we were still able to we had some really bad blobs starting off and ended up with much better blobs. And so we could look at kind of the prism microstructure and see, so here was the substrate, and then here, this spot right here was the interface, and then kind of some deposition. And so the real thing to kind of take away from this is if you look at some of these grain sizes, which are kind of hard still to see in this picture, the grain size is still a little comparable, which is good. That means it's going to be mostly homogeneous through the entire print. And you can also see these black spots here were porosity, and so the porosity is minimal. It was something that I was happy with. I mean, there's like a spot here and kind of a spot here, but the porosity for the most part was minimal enough that we were able to keep moving forward. Right. So the biggest thing in my research was to try and make this new end effector and create a system to basically a stepping stone for TIG printing. And so did I perfect it? Totally not. Given more time, maybe I could. But we characterized and just kind of wanted to see where we could get, right? And so the Z resolution is very fine, 0.36 millimeters, the Y resolution, 0.5. So and the depositions have the capability to be very clean, and no surprise, right? The savings compared to other printers that the printed metal were, 98% savings, right? So commercial printers are very expensive, but this has a lot of work to go until it's to the point where it can really compete with the commercial printer. One of the biggest things is so creating a slicer, which is something I'd shown you guys in a previous video of something that was kind of after this. So creating a slicer that can work with a single direction is something that we needed to do. And in addition to that, I think that having a rotating bed might be a helpful thing. It would be definitely a big modification. It allows us to print in any direction. The biggest thing that I think needs to really happen is when you have this arc, you have this thing called a hot spot, which is kind of like this white area of the arc, which is the highest energy, and that's usually where you want to feed your wire. Anyways, and so that quote-unquote electricity always goes the path of least resistance. Well, it distributes across all paths, but it mainly goes the path of least resistance. Anyways, so that hot spot moves depending on the conditions around it. And so when it's just a flat substrate, it's pretty much going to go straight down. But if you have another line right next to it, it's going to slightly deflect toward that line, which means that it's not where you originally assumed it was. And so that means the wire is no longer being fed into the hot spot. So what I think needs to happen, right? I've already got the data acquisition and the sensors to tell me if a weld is good or bad. What I think needs to happen is this whole feeder needs to be hooked to some sort of servo motor that automatically adjusts the angle to keep inside of that hot spot. So that's kind of my recommendation to improve this and keep the weld quality, at the level that we want. Yeah, so that was kind of in a nutshell what I did, at least with regard to metal 3D printing for my PhD research.